Hi again. My name is Ken Griggs, and I am continuing on, I believe this is the 5th video, with our discussion about PhOENIX, the physics of entanglement, networks, and information exchanges. Where we are in this lecture series is on the mathematics. How do we translate the diagrams? How do we translate all of this stuff that we've sort of visually created into a mathematical scheme? The main thing to realize is that this theory is a combinatoric theory. So one of the, and combinatoric basically means that you are using vertices and edges in order to, and faces as well, but vertices, edges, and faces in order to define a structure, and then to define how that structure changes or doesn't change. What are the conserved quantities of the structure? So in that respect, the combinatorial nature enables me to use the language of matrices to adequately define these structures. And so what I want to do is to define, or is to teach you how to define a matrix that is associated with our graphs, which basically then means with our particles. The first thing to note is that this space, the domain that we work in, is what I call a vertex space. So the number of vertices, in fact, defines how large your matrix is. Another thing to note is that the vertex space is a square space, meaning that when we define how vertices interrelate to each other, that basically means we start with a vertex and we end with a vertex. So it defines a square space. In other words, if we've got 3 vertices, then we want to know how each one of those vertices talk with each one of those other vertices. So our space is a 3 by 3 space. We can make those associations from one vertex to another. And also, I want to note that for these particles, the matrix, or the vertex space, the v-squared space, is in point of fact a real matrix and a symmetric matrix. So let's get to that. So in essence, how you set up a graph. Okay, so just really quickly, let me also state that what we were doing in the other episodes is really to talk about how to define the smallest unit, a single vertex, in this graph or combinatorial space. That single vertex can sometimes be a graph all on its own, meaning that the vertex only connects to itself. But many more times, that vertex is going to need to connect to another vertex to, in fact, form a graph that exists in and of itself. Now, and exists in and of itself just means that it's completely connected to itself. We accomplish the matrix translation of the graph by making the following associations. We will assume, and this is borne out not just out of assumption, but I will demonstrate later why this makes sense. But when you have a vertex that's connected to itself in a positive manner, meaning it forms a loop, then we will put into its matrix at the 1, 1 location. That is, that the vertex 1 is speaking to itself, vertex 1. We'll put in a +1. And in the case of an arrow, where a vertex has an arrow on it, or the anti-version of the positive or the loop, so the vertex is speaking to itself but in a negative sense, we will put a -1, okay? So it looks something like this, okay? So when you've got a loop on a vertex, it gets a +1. When you've got an arrow, it gets a -1. When you've got two loops, you just add them together. So two loops on a vertex means that we have a +1 plus a +1 or a +2. Two arrows on a vertex means we've got a -1 minus 1 equals -2. Yeah. Pretty simple. And the same thing happens when we've got three loops on our vertex. It's just +3 from our previous rule, and three arrows on a vertex are just -3. So basically, whatever's sitting on a vertex adds together to form the result of what's sitting on that vertex. Okay. So, if we have two electrons, or let's say an electron and a positron, and I will remind you that an electron has 3 loops on it, and the positron, its antiparticle, has 3 arrows on it. So, to form the matrix, the first thing we do is to label which vertex we're talking about. So in our case, right here, for the electron, we've labeled it 1, and for the positron, we've labeled it 2, right here. So in that case, you know, we've got electron 1 here and positron 2 here. But in this case, when we come to our matrix structure, we're going to be calling, we're going to have a first column, and we're also going to have a first row. So we're going to put the label of 1 above the column and the row, and the label of 2 above the appropriate columns and rows as well. See that? Okay, so one way of doing that is just to literally draw some lines in there so that we know that in our matrix it's a 2 by 2 matrix. So in our 1-1 slot we have something, in our 1-2 slot we have something that, in our 2-1 slot right here we have something, and in our 2-2 slot we also have something. Now in this case, because our electron on vertex 1 has 3 entities on it, 3 loops, then from our previous rule, right here, from our previous rule, we know that the number associated with it is a +3. So we're just going to stick in slot 1-1, a +3, because again, the vertex 1 right here has 3 loops on it, right there. So we get to call that a +3. Now, in slot 2-2 right here, what we're asking is, how does vertex 2 talk to itself? And from our previous, again, arrangement, because we're dealing with arrows now, it's a -3. Now we have the extremely important question of how does vertex 1 talk to vertex 2? And the answer is, the only way they talk is when there's actually an edge connecting the vertices. And in this case, there are no edges, so they don't talk. So in our case, the answer would be 0. So we would say that 1 communicates with vertex 2 in a 0 way. So 1-2 here would be 0. And we can also ask the same question in reverse. How does 2 communicate with vertex 1? And again, just like in the previous case at 0, it's also 0 in that direction too. So here is also 0. So we've just written out a matrix that completely defines this 2-particle system right here, the electron and the positron. And that matrix has a 3, 0, 0, right here, -3. So that completely defines that system. Let's deal with something slightly more well, maybe not more complicated, but let's deal with something where we have a photon. And in fact, let's form the photon that in fact forms from this system. We're going to stay on our same sheet of paper, but the photon, as you recall, looks like that. Now we're going to label the vertices as we have above as 1 and 2. Okay? We're just going to call that the gamma or the photon. And as we define its matrix, which is also a 2 by 2 matrix, obviously, because remember, in this theory, the number of vertices is conserved. So when our system starts off as a 2-vertex system, it always ends up as a 2-vertex system. Vertices don't disappear or appear out of nowhere. So that's very important to know. It's a conserved quantity in this way of doing PhOENIX. So in this way, we're establishing a matrix here, a 2 by 2 matrix with 4 slots to fill. And the question we ask is, on our particle here, right there, on vertex 1, how many loops or arrows are there? The answer is 0. So vertex 1 is not connected to itself in any way, shape, or form. So in slot 1, 1 goes a 0. Now equally in vertex 2, we ask the same question. How self-connected is it? The answer is it's not connected to itself at all, so the answer is 0. Which means that in slot 2, 2, we also have 0. All right, that was easy. So the translation between the graph and the matrix is in fact very direct. There's just no ambiguity about it. Now, we also ask the question, how is vertex 1, right, it's always tough doing it this way, but how is vertex 1 connected to vertex 2? Well, like we do with the self-connection, here we've got, it's connected with 3 edges, okay? Boom, boom, and boom. And 3 positive edges at that. So in the 1, 2 slot right here, we put a +3. Now equally, for the reverse situation where we ask, how is 2 connected to 1, it's connected in the same way. It's 3. So in our bottom slot here, right there, it's also a +3. So you see how these rules are coming about. Literally, you ask, well, add up the edges. How many edges, you know, are going from one vertex to another? How many edges connect those 2 vertices? And that's the number that you put in the slot of the matrix. How self-connected is a vertex? And that's a slot. That's the number that you put in to that slot of the matrix. Okay, so we've got 2 matrices now. And I'm really getting sick and tired of this camera moving, but so I'm going to stop the camera from moving because it's really irking me. Okay, so give me 1 second here. That would have been... Follow my face. Okay, there we go. Okay, so now you guys see the 2 matrices, right? And the 2 systems that they describe. This describes a positron and an electron and a positron, and this describes a photon. So this is the first step of the mathematics. That is, you define a system of particles or a single particle according to a matrix. Now, we see here that there are 2 independent particles. And you'll notice that there are 2 of these, it's a diagonal matrix, and they're separated by zeros. Okay, that is to say that these 2 particles are not connected to each other in any way, right? That's where those zeros come from. So you can always create a system of particles, but how they're separated from each other, or with zeros on the diagonals, okay? Whereas here, what we have is a system that's fully connected to itself. And in this case, it has nothing, it has no self-connection, so it's got zeros along the diagonal, and its its interaction, you might say, between vertices is covered by these edges right here, defined as the off-diagonal elements. So this is what our matrix looks like. This is what a PhOENIX graph looks like matrix-wise. So the next thing that you need to know is how, and that's what we call, by the way, the state of our system. Each one of these matrices defines the state of a system, exactly what the system looks like at one moment in time. Okay? Now we need to define a dynamical equation, an evolutionary equation. Has one state become something else? Okay? And the realization was that, or has been, that the equation that defines how two states relate to each other, or better yet, how you make one state become something else, is what we call an orthogonal transformation. It is what we also call a similarity equation. So a similarity equation looks something like this. Okay, so just to let you know, I'm going to call the first matrix, let's just call it chi1, and the second matrix we'll call chi2. Now, the Greek terminology here has just become standard practice for me to call it a chi1 and chi2. So I know if this is new for you using these Greek symbols, just call it A, the first one, and call the second one B. But I use the chi, so I want to make that standard for you. Okay, chi is also important because it looks like X, and in point of fact, these particular matrices represent the spatial locations of these objects, of these little bits of information, of these particles. So that's why I used sort of a Greek variant on the idea of X. And for me, it's chi because they look similar, but I just wanted to put that out there for you. So our equation that allows us to transform from one state to another, from one system of particles to another system of particles, is our evolution equation, which looks like this. That's our equation. It's a similarity equation. Okay? Now, essentially what our equation is saying is that if we start off in a state 1, there is some system of transformation, some other matrix that on the one side multiplies on the one side by that transformation matrix and multiplies on the other side by its transpose. And when we have this situation, it produces our second state, or our new state, which is our product state. And so this is our evolution equation. Now, because our matrices are both real, integer, but in particular because they're real, our matrix here, our T's, our transformations, okay, are in point of fact what we say orthogonal. An orthogonal transformation basically means that the transpose of it is in fact equal to the inverse of it. Okay? That's almost the definition of orthogonal right here, that the transpose of it equals the inverse of it. So all of these things are matrices. In fact, they're all square matrices, meaning that the number of rows is equal to the number of columns. So I'm not wanting to dance you through matrix algebra. If you do have questions on it, certainly pick up a good matrix book or look it up on YouTube, or look it up as well, Google it, and you'll find a lot of great texts on how to perform matrix manipulations, matrix algebra, etc. I'm just sort of trying to get you to the actual mathematics that that will enable us to work and to demonstrate what I've been talking about before, but haven't been able to mathematically demonstrate for you. So in this particular case, we see that our governing equation, this top one, is a similarity equation that these things here, the states 2 and 1, fully and equal and easily define the graphs and the system of graphs, and that they're square matrices and that they're real. Okay, so that property means that this similarity equation has transformations that are orthogonal. Okay, now these orthogonal matrices are also real. So I'm going to say they're orthogonal and they're real, meaning that there's no complex numbers going on. Okay, we don't have to worry about the imaginary number in any way, shape, or form here. Now, in this theory, these transformation equations, I give them the T, yes, because it, says transformation, but T also because they represent time. They represent units and steps in time. And these matrices, these chi's, chi1 and chi2, these states, these graphs, actually represent space. So in this equation, we actually have an association between space, the two spatial states, and the two time states. Okay? So we have an association of how time and space actually interrelate in a dynamical sense, because that's what a dynamical equation is, an evolution equation. It's something that takes you from one space and transforms you into another space. So that's our fundamental equation. And so one of the properties of this equation is that one of the conserved properties of the equation is that the characteristic equation of that equation is conserved. Now, the characteristic equation is a long, drawn-out way of talking about eigenvalues and eigenvectors. It's a long, drawn-out process of talking about taking a matrix and making it into a scalar. But from whatever angle you want to use to talk about it, it's a property of a matrix. And if that matrix is undergoing an orthogonal transformation, it is a conserved property of that system of matrices that work for that evolution equation. So one can talk about the characteristic equation that's associated with the matrix. And so what I'm basically saying is that the matrix will always be transformed into another matrix that has exactly the right characteristic, the identical characteristic equation. In other words, they share the same eigenvalues. Okay. Now, something to also note is that our transformation matrix, our orthogonal transformation matrix, which is real, completely defines what will and what will not happen in our system. Okay? So, essentially, our equation asks or says that in order for a transformation to occur, the input or the initial state must be a graph, a system of graphs that have the properties that we've been outlining for the last 4 lectures. And it must be transformed into a system of graphs that also have the properties. Now, in particular, the property that I'm talking about is that the graph itself is a bona fide graph, okay? It's not an incomplete graph. The graph, every vertex on that graph has 3 of something. And every vertex is connected to another vertex to form a complete graph. And so the complete graph structure has to be borne out in all of the proper states of our system. There can be no And let me just draw it out for you. But you cannot have a system that looks like this. You can't have this. And so what I'm demonstrating here is that on the one side here, we have an electron. We have a U quark and we have a D quark. The electron is fully contained. It is a complete graph in and of itself. It needs no other vertices to connect to. But this graph, the U quark, in fact needs to connect to another vertex. But it isn't. It's not represented here as connecting to another vertex. That's what we call an incomplete graph. So this is not allowed as a particle. This does not exist in and of itself as a particle. A particle is only defined as a complete system, a complete graph. And this one over here, the D quark, has the same problem. It needs to connect to either two vertices or doubly connect to a single vertex, in which case it can become a complete graph. So that's what we're trying to outline here. The matrix representation says that this has no matrix representation. This is a meaningless system of graphs. The only thing that has meaning is this one here. And so that's what I'm talking about when I'm saying that you start off with a state that has a meaningful set of graphs, and you end up with a state that also has a meaningful set of graphs. And those graphs we call particles. So the initial state has only particles, and the final state has only particles. And the transformation matrix, the T matrix, determines how the particles transmute and transform into each other. And that's a beautiful thing. So when we go to, let's do the neutrino. That's a good one. So when we go to the neutrino, we're going to define the two, actually we're going to do the neutrino next. We're going to go back to the photon, because that's the reason why we did the matrices the way that we did. Recall that the photon here has this matrix here, okay? And then the electron and the positron here have this matrix here. So we want to demonstrate that there is a transformation that actually exists between the two. That this can in point of fact become this, and this can in point of fact become this. And the easiest way of demonstrating that is by showing that they actually have the same characteristic equation. So I'm going to just really quickly, and again, you should look this up online, what is the characteristic equation and how do you get it? But it is a monomial. It is a single variable equation that is filled with scalars. It is not a matrix. That's the key about a monomial, and that is the key about the characteristic equation. It's an equation that defines the matrix, but it is in and of itself not a matrix. So for the electron and the positron, I'm going to just find the characteristic equation for you. By the way, the definition of it is you take the determinant of your graph subtracted from a parameter called the eigenvalue times the unit matrix of the size of the original matrix. So that is how you get the characteristic equation. And in order to find what the eigenvalues, the lambda values are, you set this equal to 0. So what we're going to do is to find this characteristic equation, as I've said, for the electron-positron or chi-1 matrix. So the first thing we do is we write out the matrix. Okay. Actually, let me stop it here and we'll come back to this.